In this class, we will discuss about nuclear reactors. A nuclear reactor is a device for releasing nuclear energy through fission at a controlled rate. It is also known as a chain reacting pipe. The chain reaction is a self-sustaining process that, once started, needs no additional agents to keep it going. Thus, to maintain a chain reaction, the neutrons must be produced at a constant rate and the number of neutrons released per fission must be sufficiently greater than 1 to compensate neutron loss. The achievement of chain reaction with the uranium, normally uranium-235, depends on a favorable balance among following 6 processes. When you take 235, it is a mixture of normally 235 and 238. So, neutron may be absorbed by uranium-238 and may cause a fission when neutron energy is greater than the threshold energy. This is because normally this uranium-238 is not fissionable. And neutron may be absorbed by uranium-238 without producing fission. And neutron may be absorbed by uranium-235 causing a fission, or as the fourth point, uranium may be absorbed by uranium-235 without causing fission. Neutron may be absorbed by other materials present in the assembly. That means they will not cause fission. And neutron may escape without being captured. So these are the 6 possibilities. And the processes 1 and 3 create new neutrons, while other remaining processes remove availability of neutrons from the assembly. So actually a particular fission starts with a single neutron. And when additional neutrons are produced inside the core, then only you can continue the reaction. We will not supply neutrons continuously from outside. The neutrons required to continue the reaction are produced within the core itself. So, in order to have a continuous chain reaction, there must be a nuclear balance. And this nuclear balance can be described in terms of a cycle that shows what happens to the neutrons. The number of fast neutrons produced by each thermal neutron absorbed by the fuel is called thermal fission factor and is denoted by eta. So, when this 235 is absorbing neutron, it is producing fast neutrons. That means with high energy. So, you are defining this thermal fission factor eta as number of neutrons produced by fission by number of neutrons absorbed by fuel. Consider this cycle starting with the fission of uranium-235 nucleus by a thermal neutron. Normally thermal neutrons are with low energy of the order of 25 MeV. Let nu be the number of fast neutrons which are emitted in this fission. Some of them having energy greater than the fission threshold for uranium-238 can cause fission in uranium-238 with a subsequent increase in the number of fast neutrons. The total number of fast neutrons from fission is thus increased from nu to nu epsilon, where epsilon is greater than 1. Initially, you have a particular 235 fission, new number of neutrons are produced, and they are causing fission in uranium-238. And from the fission of uranium-238 to actually thorium, plutonium, etc., number of neutrons are produced. They are also fast neutrons. And the total number of fast neutrons from fission is thus increased from nu to nu into epsilon. So epsilon is a factor which must be greater than 1. And this epsilon is called fast fission factor. Fast fission factor you are defining as total number of neutrons from thermal and fast fission. And the denominator, you have fission neutrons from thermal fission. So this is the first neutrons produced, and this is multiplication. From a finite size reactor core, some fast neutrons may leak out before being slowed down to thermal energies. So the first two things, this thermal fission factor and fast fission factor, shows the number of neutrons that are produced. Now we will discuss the neutrons that are losing. So neutrons may leak out, and to account for this, the leakage factor for fast neutrons is introduced. The remaining fast neutrons in the core are slowed down by collision. So you have a large number of fast neutrons produced, and some of them are lost. So you will consider a lost leakage factor for that, and there will be remaining fast neutrons. And from this remaining fast neutrons, we are slowing down them to become thermal neutrons, and this is done by moderators. And the process of, or the reason for the slowing down is to use these neutrons as thermal neutrons for making fission to uranium-235. And during the slowing down process, some of them may be captured by uranium-238 to form uranium-239, which then decays. So before the slowing down, some is captured by uranium-238. And this decay is particularly at energies in the region of strong resonance. And this 239 is not decaying with the emission of neutrons. So this decay is particularly at energies in the region of strong resonance. And this is a term related to your nuclear reactions. And this resonance is, if a target nucleus is bombarded with particles, it is sometimes observed that the nuclear reaction takes place with appreciable probability only if the energy of the bombarding particle is in the neighborhood of a certain definite energy values. And these energy values are referred to as resonance energies. So, the energy of neutron is somewhat equal to the resonance energy of this uranium-238. That is why it is causing fission, or it is capturing. The nuclear reaction is taking place. So some neutrons, before slowing down, they may reduce due to this capturing by uranium-238, and it is the process of resonance. So we introduce the resonance escape probability P as the ratio of the number of neutrons slowing to thermal energy to that of total number of fast neutrons available for slowing. So we have total number of neutrons available, and from this a small factor is making resonance. So resonance escape probability is number of neutrons flowing to thermal energy, and the number which are lost due to this resonance is decreased from the total number of fast electrons, and you are getting a factor, and normally this will be less than 1. So number of neutrons flowing to thermal energy to ratio total number of fast neutrons available for slowing. And the neutrons which escaped are slowed down to thermal energies. That means without this resonance capturing, some of the which are escaping, that means it is not escaped from the core, that means they overcame and they are not undergoing this process. So they are ready to slow down. Some of these thermal neutrons may leak out of the core. That is also a probability. And to account for this, we introduce the leakage factor for thermal neutrons. And a fraction of, so you have a number of thermal neutrons produced. And from these thermal neutrons, some number is absorbed. And for that, we have the resonance condition. So resonance absorption factor you have considered, and from that a small number is losing by leakage, and in the remaining one some number may be absorbed by other materials and the balance by uranium. So the fraction of thermal neutrons absorbed by the fuel as compared to all other neutron absorptions in the assembly is called thermal utilization factor, because the number absorbed by uranium can cause only fission. So that is why that number, so if this number is large, more probability for fission. So that is thermal utilization factor, as thermal neutrons absorbed by the fuel by total thermal neutrons absorbed. If we introduce this term, we obtain the number of thermal neutrons that are actually absorbed by the fuel. Not all the neutrons absorbed by the fuel can cause fission. Some are absorbed by uranium-238, while others are absorbed by uranium-235 to form 236. The final number of second generation neutrons absorbed in the fuel is known as reproduction factor or multiplication factor. It is denoted by K. Again that term. First, a neutron is causing fission and a number of neutrons are produced there. And from they are known as the second generation or in current generation, which is produced by the previous generation, and these neutrons can cause fission to other nuclei, so they can produce neutrons. So in that case, current generation means the neutrons which are produced by the neutrons which are causing the fission, and they are in the previous generation, and that is denoted by the letter K. K is the number of neutrons in current generation divided by number of neutrons in previous generation. So we have these terms: multiplication factor K as number of neutrons in current generation by number of neutrons in previous generation, and thermal fission factor eta as number of neutrons produced by fission by number of neutrons absorbed by the fuel. And fast fission factor is total number of neutrons from thermal and fast fission divided by fission neutrons from thermal fission. Resonance escape probability P as number of neutrons slowing to thermal energy by total number of fast electrons available for slowing, and thermal utilization F as thermal neutrons absorbed by fuel by total thermal neutrons absorbed. So you have these 5 terms and they can be connected as. So neutrons are increased in 2 ways: thermal fission factor eta and fast fission factor epsilon, and they are absorbed in 2 ways: the resonance escape probability P, and thermal utilization factor F. The way in which neutrons are increased and absorbed can be described by a combination of these four factors and is known as the four-factor formula. You have four factors. That is why we have normally written them as factors. Sometimes it's also known as resonance escape probability factor. So, by connecting these four with the fifth one as K, you have a formula known as the four-factor formula, or sometimes Fermi's four-factor formula. And if the core is of very large size, the multiplication factor can be denoted as K infinity. The four-factor formula is then given as K infinity equal to eta epsilon Pf, where the first two terms is the number of increasing factors, thermal fission factor eta, fast fission factor epsilon, and then resonance escape probability factor P, which is decreasing number of neutrons, and thermal utilization factor F. And if this is not K infinity, that means for finite size, you have to consider some other loss factors also in this equation. And this actually we have mentioned. You have fission neutrons, and these fission neutrons are getting as fast neutrons, and some of these fission neutrons are causing fission to other, that means uranium-238 can be only thermal neutrons can cause fission to uranium-235, but some neutrons, that means these fast neutrons can cause fission to uranium-238, but at a particular condition. So, you will be getting a more number of fast electrons, and from this, for this we have introduced the term this one. Fast fission factor epsilon. So this is for here you are getting that, and out of this a small number is escaping, and again you are slowing down to moderators, and from here also some number is missing. Then it is absorbed by the fuel, and from fuel also there will be some loss. So finally you are getting this number of slow neutrons to cause fission. We have introduced so many factors here, and this is actually we have discussed, that is shown in this schematic representation. In an infinite system, the condition for the self-sustaining chain reaction is that each neutron generation just replaces the previous one. That is K is equal to 1. The system is then said to be critical. So, if one is lost, it must be reproduced. For a finite system, because in each neutron generation, some neutrons are lost from sides of the system, the critical condition is that K must be greater than unity. The exact amount by which it has to be greater than unity depending on the shape of the system and the arrangement of the materials in the system, etc. If K is greater than unity for the infinite system, the number of neutrons will increase steadily and the chain reaction is called divergent. It is continuing. I think you have drawn that figure of chain reaction from a first one, 3, then that 3 to, from each 3 you will be getting 9, 27. So it is multiplication and it is diverging from a point, you can increase it. That is why it is a called divergence, and the system is known as supercritical state. So for an infinite system, when k is equal to 1, it is known as critical. When k greater than 1, supercritical. And when k less than 1, it is known as subcritical. So the number of neutrons would decrease to 0 and no chain reaction is no chain reaction is possible. And this is known as subcritical case. And the general aspects of reactor designs are, this is already known to us. In spite of numerous possible variations in design and components of reactor system, there are a number of general features which all reactors possess in common. And they are, this is the schematic representation of a reactor. You can see fuel, core, this is a reflector, shield, control rods, coolant, heat exchanger, etc. And the schematic representation of a nuclear reactor system is shown in figure. A reactor consists of an active core in which the fission chain reaction occurs. The core contains the nuclear fuel consisting of a fissile nuclide. A fissile one means which can be made fission. The high energy neutrons liberated in the fission process are slowed down by moderators. The fuel elements are arranged in a regular pattern with the moderator. The fuel moderator core is surrounded by a neutron reflector to reflect neutrons back into the core and to minimize the neutron leakage. The heat generated in the core due to the fission process is removed by circulation of a suitable coolant. If the energy released in the reactor is to be converted into electric power, the heat from the coolant is transferred to a working fluid to produce steam or hot gas. The steam or hot gas is carried to the heat turbine, which is connected with the exchanger generator to produce electricity. And we will discuss the parts. First one is fuel. The material containing the fissile isotope is called the reactor fuel. The fuels that can be used are uranium containing 235, that means U35 in its natural concentration of 0.715% or in an enriched proportion. That means you will be just increasing that. The remaining 99.3% being uranium-238 and it is called fertile material. That means it is not fissionable, but you can make it fission. That is why it is known as fertile. It can be converted to fissile, plutonium-239 by the following reactions in a reactor. This process of change from a fertile to fissile material is termed conversion. The number of fissile nuclei produced per fertile nucleus burned is called conversion factor. Next is moderators and reflectors. Materials used to reduce the neutron energy are known as moderators. Examples are graphite, light water, heavy water, beryllium and its oxides, and certain organic compounds. The critical size of a reactor can be reduced by surrounding it with a good moderating material as reflector. That means it is not, so these reflectors are to reduce the loss in neutrons. So it must be a good neutron scatterer and does not usually absorb neutrons to any great extent. Graphite is often used as a reflector. And reactor coolants. The material employed to remove the heat that is being generated in the reactor core as a result of fission are known as coolants. These materials are circulated through the core for the purpose of extracting the heat and transferring it to the outside of core. The materials proposed for coolants are ordinary water, heavy water, etc. Next is control materials. In thermal reactors, control is achieved by means of neutron absorbing materials. The material should not become radioactive as a result of neutron capture. Because of its availability and ease of fabrication, cadmium was used as this control materials in olden days. It can be utilized at low temperatures work only because it has low melting point. As you know, in a reaction, heat is generated, so there is a possibility for melting this control materials. Now, the most common neutron absorber used for reactor control is boron. This element has very high melting point and large cross sections for neutron absorption. Boron is often used in combination with stainless steel, aluminium or carbon. The control elements are commonly located in the core in the form of either rods or plates. That is why we have a general term as control rods. Now, reactor shielding. All nuclear reactors except those operating at very low powers are sources of intense neutron and this is a gamma radiation. Why? And therefore represent hazard to persons in the immediate vicinity of the reactor. Provisions for their health protection are made by surrounding the reactor core with a radiation shield. This shield is generally known as the biological shield because its primary function is of health protection. It consists of generally a layer of concrete which is about 6 to 8 feet thick and is capable of absorbing both the gamma rays and neutrons. And in selecting materials of reactor applications, the general characteristics are it must be of good mechanical strength, ductility. It should be ductile, that means it should not break easily. Stability, availability, it should be an easily available one. Fabricability, that which can be molded in any way. Corrosion resistance, it should not be get worse or it is not corrosion. Heat transfer and cost. The additional facts in selection of reactor material are neutron absorbing capacity, susceptibility to induced radioactivity. These materials should not cause a radioactivity and radiation stability, etc. And we have already discussed a nuclear reactor. There are so many ways to classify them. The first method is based on the manner in which fuel and moderator are mixed as homogeneous and heterogeneous. In a homogeneous reactor, the fuel and moderator are mixed in the form of a solution. And most of the nuclear reactors are of heterogeneous size. In heterogeneous reactor, fuel is concentrated in plates, rods or hollow cylinders which are distributed in a regular pattern or lattice within the moderator. And this type of heterogeneous reactor we have drawn in our figure. And reactors can be classified according to the energy of neutrons that cause fission. So, these reactors are known as thermal, intermediate or fast. So, a thermal reactor means the fission is caused by thermal neutrons. Intermediate neutrons causing is intermediate reactor. So, fast reactor means or fast breeder reactor is it is causing by fast neutrons. And the energy ranges are for thermal neutrons 0.025 electron volt, that means 25 MeV. For intermediate neutrons, it is 1 to 10 keV, kilo electron volt, and for fast neutrons, the energy should be greater than 10 keV. And reactors are also classified according to their purpose. They are research reactors, production reactors, and power reactors. A research reactor means this is used for research purposes in nuclear fission and also for in medical purposes and for producing radionuclides, etc. You are using this research reactors. And these production reactors are mainly used for making a fertile material to fissile material. And power reactors they are used for power generation. That is a nuclear power plant. And that's all about your nuclear reactor. Thank you.